Dear friend, welcome to this gentle journey through the frontiers of quantum gravity, a space where the smallest particles and the vast cosmos intertwine in a dance of possibility. Let your mind drift as we explore the quiet mysteries of space-time, where each ripple and fluctuation tells a story of our universe's hidden unity. Find a comfortable place and let the soft flow of words guide you into a state of calm curiosity. Let's begin. Chapter 1. The Challenge of Unifying Physics. The quest to unify the fundamental forces of nature has been one of the most profound and persistent themes in the history of science. From the earliest days of contemplating the motion of the planets to the delicate structures of atomic particles, we have sought a single, coherent framework that could describe everything from the grand arcs of galaxies to the subtle dance of subatomic particles. This journey has brought us to a crossroads, the need to reconcile two of the most successful and yet apparently incompatible theories of physics: general relativity and quantum mechanics. General relativity, Einstein's monumental insight, reimagined gravity not as a conventional force but as the curvature of space-time itself. In this elegant formulation, massive objects warp the geometry around them, guiding planets along curved paths and causing starlight to bend as it passes near them. Gravity, in this picture, becomes the very shape of the universe, a smooth and continuous geometry that evolves as mass and energy shift across the cosmic stage. Quantum mechanics, by contrast, describes a world that is anything but smooth. At the tiniest scales, it reveals a universe of probabilities and uncertainties, where particles exist in a haze of possible states and interactions are governed by discrete quanta. Here, measurement itself becomes a central player, collapsing the shimmering possibilities into concrete outcomes. This quantum realm, so successful at describing atoms and molecules, underlies the very processes that power the sun and give structure to matter. For decades, these two theories have stood as the twin pillars of modern physics, each astonishingly accurate in its own domain. General relativity commands the cosmos, mapping the orbits of planets and the expansion of the universe. Quantum mechanics reigns in the microcosm, explaining the behavior of electrons and photons with unparalleled precision. Yet despite their individual successes, they remain curiously at odds, like two languages describing the same world with fundamentally different alphabets. The tension becomes unavoidable when we probe the extremes of nature, regions where the intense curvature of space-time predicted by general relativity must meet the restless uncertainty of the quantum world. One such region is the heart of a black hole, where gravity becomes so fierce that the classical description of space-time predicts a singularity, a point of infinite density and zero volume. In this scenario, the usual smoothness of geometry breaks down, and quantum mechanics whispers that no measurement can be infinitely precise. The clash between the continuous and the discrete signals that neither framework, on its own, can tell the whole story. A similar puzzle arises when we look back to the very beginning of the universe. The Big Bang, as described by general relativity, emerges from a singularity, a moment of infinite density and temperature. But at such extreme conditions, the quantum properties of the fields that fill space cannot be ignored. The early universe was not a smooth, continuous expanse, but a cauldron of quantum fluctuations, where the geometry of space-time itself was uncertain and dynamic. Without a theory that unites these two pillars, our understanding of the cosmos's birth remains like a half-finished tapestry, rich in detail but with crucial threads left hanging. The need for a deeper theory is more than an intellectual puzzle. It reflects the underlying unity of the universe itself. Nature does not operate in separate compartments. There is no dividing line between the motion of the planets and the spin of an electron. The same reality shapes both, And so the search for a single unified framework is not a mere curiosity. It is a necessity, a demand imposed by the seamless interconnectedness of the world around us. Early efforts to bridge the gap between gravity and quantum mechanics gave rise to quantum field theory, a framework that describes the other fundamental forces of nature with extraordinary precision. In this formulation, forces arise from the exchange of particles, like photons for electromagnetism or gluons for the strong nuclear force. Quantum field theory has passed every experimental test, confirming that at its core, nature is woven from fields that fluctuate and interact in a quantum dance. Yet when gravity is treated in the same language, something unusual happens. The mathematics of quantum field theory, so successful in describing other forces, begins to falter. Infinities arise that cannot be renormalized away, and predictions lose their meaning at the very scales where quantum gravity is most needed. This suggests that a deeper theory, one that goes beyond the familiar methods of quantum field theory, is required to fully capture the quantum nature of gravity. Physicists have proposed a range of possibilities for what such a theory might look like. Some suggest that space and time themselves are not fundamental, but emerge from a deeper quantum structure, a network of relationships, rather than a fixed backdrop. Others propose that gravity is not a fundamental interaction at all, but a kind of statistical effect, a manifestation of how information and entropy flow through the universe. Still others explore the idea that space-time at the smallest scales is a seething foam of quantum fluctuations, a dynamic environment where geometry itself becomes uncertain and restless. These visions share a common thread. They challenge us to rethink what it means to measure, to observe, and even to exist. In the world of quantum gravity, the familiar notions of distance and duration may not be absolute. They might be statistical averages of countless quantum processes, ephemeral at the smallest scales, but coalescing into the smooth structures we see in the sky and in our laboratories. The search for quantum gravity is not simply about tweaking a few equations or adding extra terms to familiar theories. It is a reimagining of what it means for the universe to have shape and structure. It asks us to see the geometry of space-time not as a passive stage, but as an active, living participant in the cosmic drama. It suggests that the very flow of time, so deeply woven into our experience, might itself be a consequence of quantum processes unfolding in a deeper layer of reality. Clues to this deeper layer come from many directions. Observations of black holes, of the faint afterglow of the Big Bang, and of the ripples of gravitational waves all hint at the unity of gravity and quantum mechanics. These observations do more than test our theories. They inspire new ones, opening windows into realms where even the quiet geometry of empty space is alive with possibility. The discovery of gravitational waves, for instance, has shown that space-time can ripple and flex like a living fabric. These waves, generated in the titanic collisions of black holes and neutron stars, carry with them a silent song, a story of the universe told in the vibrations of space-time itself. They remind us that gravity is not a static presence but a dynamic field, one that pulses and shifts as mass and energy swirl across the cosmos. In the faint echoes of these waves, some physicists hope to find the subtle fingerprints of quantum fluctuations, hints that even the grandest motions are shaped by the restless interplay of the quantum and the cosmic. This interplay also forces us to reconsider our methods of calculation and measurement. The mathematical languages of general relativity and quantum mechanics, each so successful on its own, speak in different dialects. General relativity describes a continuous, curved geometry, while quantum mechanics speaks in terms of probabilities and discrete events. Merging these into a single coherent framework is a challenge that has occupied some of the brightest minds in physics for generations. The search for this unified framework is driven not just by a desire for mathematical beauty, but but by the conviction that the universe itself demands it. Each observation, each anomaly in the data is a whisper from the cosmos, a hint that our current understanding is incomplete. And each new idea, whether it be strings vibrating in higher dimensions or loops of quantum geometry, is an attempt to listen more closely to those whispers. Yet in the face of this uncertainty, there is a kind of quiet wonder. The effort to unify physics is a testament to the creativity and persistence of the human spirit. It reminds us that knowledge is not a final destination, but a journey, a constantly evolving story that we write with each new observation and each new equation. It is a story that binds us to the universe in the deepest sense, showing us that our questions and our dreams are part of the same restless motion that shapes the stars and the spaces between them. As we stand at the edge of this frontier, the dream of a unified theory continues to beckon. It calls us to explore the hidden connections that tie together the vast and the minute, to seek the threads of unity in the tapestry of existence. In this search, gravity becomes more than the force that holds us to the earth. It becomes a bridge between the world we see and the shimmering possibilities of the quantum realm. In the quiet interplay between the certainty of geometry and the flickering uncertainties of the quantum, we find not frustration, but a profound sense of wonder, a reminder that the universe is both more mysterious and more deeply connected than we have yet begun to imagine. Chapter 2. The quantum nature of space-time. The quest to unify our understanding of the universe has brought us to a startling realization. Even the very fabric of reality, space and time themselves, may be subject to the unpredictable rhythms of the quantum world. In the classical view of general relativity, space and time form a continuous backdrop against which the drama of the cosmos unfolds. Distances are smooth and measurable, and time flows in a steady progression, from the ticking of seconds in a quiet room to the eons that stretch across the lives of stars. This vision of a smooth and predictable geometry has served us well in describing the majestic motions of planets and the gentle bending of starlight around massive objects. Yet, as we probe deeper into the microscopic realm, quantum mechanics teaches us that the universe is not so serene. At the smallest scales, uncertainty is not a flaw but a fundamental feature of nature. Particles do not follow single paths, but exist in a shimmering haze of probabilities. Measurements themselves influence outcomes, and the very act of observation shapes what we see. These quantum principles, so effective at explaining the behavior of atoms and molecules, seem at first to have little to do with the stately geometry of space-time. But as we push the boundaries of our understanding, it becomes clear that space and time cannot remain untouched by the restless fluctuations of the quantum world. This realization challenges our most basic intuitions. We are accustomed to thinking of space as an unbroken expanse, as real and solid as the ground beneath our feet. We measure distances with rulers, navigate by the stars, and trust that the geometry of the world around us is smooth and continuous. But in the world of quantum mechanics, nothing is truly continuous. At the smallest scales, distances so small they elude even the most powerful microscopes, space-time itself may become grainy and dynamic, a restless dance of geometry that defies our familiar notions of location and duration. To understand this quantum nature of space-time, we must first recognize that the geometry we experience is an emergent phenomenon, a large-scale average of countless tiny interactions. Just as a smooth sheet of water is made up of molecules jostling and colliding, the smoothness of space-time may arise from the collective behavior of microscopic quantum processes. This idea suggests that the familiar curves and distances of general relativity are not fundamental but approximate, a kind of statistical calm that masks a deeper, more restless layer of reality. Physicists have long speculated that at the Planck scale, distances on the order of 10 to the minus 35 meters, space-time itself may lose its classical structure. In this realm, the concepts of here and there become blurry, and the smooth geometry of Einstein's equations gives way to a frothy sea of quantum fluctuations. This vision, sometimes called quantum foam, imagines the fabric of the universe as constantly bubbling and shifting, with tiny loops and ripples appearing and vanishing in a ceaseless, silent commotion. These quantum fluctuations are not merely theoretical curiosities. They arise naturally when we apply the principles of quantum mechanics to the gravitational field. In quantum electrodynamics, the vacuum is never truly empty. It teems with virtual particles that flicker in and out of existence, momentarily borrowing energy from the void before disappearing again. This restless activity shapes the forces we observe, leading to subtle effects like the Lamb shift in atomic spectra and the Casimir force between closely spaced plates. If gravity is also a quantum field, it too must participate in this dance, with the geometry of spacetime itself trembling with ephemeral fluctuations. Yet these fluctuations, while fundamental, are astonishingly small, far beyond the reach of direct measurement with today's instruments. We cannot yet build detectors sensitive enough to see the quantum jitter of geometry itself. Instead, physicists explore these ideas through indirect means, through mathematical models that extend the language of general relativity to include quantum uncertainty, and through experiments that seek faint traces of these fluctuations in the relic light of the early universe or the subtle signatures of gravitational waves. One of the most profound implications of this quantum nature of spacetime is that it forces us to reconsider what we mean by geometry itself. In the classical view, geometry is a fixed and absolute stage, an unchanging framework within which matter and energy interact. But in the quantum view, geometry is dynamic and contextual, shaped by the same uncertainties and probabilities that define the behavior of particles. Distance and duration are no longer rigid measures, but fluctuating quantities, influenced by the quantum state of the geometry itself. This reimagining of geometry invites us to see space and time as participants in the universe's unfolding drama, not mere spectators. The idea that the geometry of space-time is alive with quantum possibility resonates with some of the deepest questions in physics. It suggests that the flow of time is not a simple, universal ticking, but a consequence of how quantum information is organized and transformed. It hints that causality itself, the chain of cause and effect that underpins our understanding of the world, may be an emergent property, arising from the deeper quantum structure of spacetime. This perspective is more than just a mathematical curiosity. It has philosophical implications that touch on our sense of reality itself. If the classical geometry of spacetime is an approximation, then the universe we experience is, in some sense, a projection of a deeper, more fluid quantum order. The sharp boundaries we see, the edges of objects, the separation between moments, are not fundamental but emergent, shaped by the collective behavior of countless quantum interactions that we cannot directly perceive. These ideas also suggest new ways to think about the interconnectedness of the universe. Quantum entanglement, that strange and beautiful phenomenon where particles share states across vast distances, may not be limited to particles alone. Some physicists propose that the very fabric of space-time is woven from entanglement, that the geometry of the universe is a manifestation of quantum correlations that link distant regions in ways we are only beginning to understand. In this view, the connections between places and moments are not fixed, but fluid, shaped by the hidden patterns of quantum information that underlie the smooth surfaces we see. The challenge of describing this quantum geometry lies in the fact that our traditional mathematical tools were never designed for such a task. General relativity speaks the language of smooth curves and continuous metrics. Quantum mechanics speaks in the probabilistic language of wave functions and operators. Reconciling these languages, finding a mathematical framework that can capture the flickering quantum geometry of space-time, has proven to be one of the most formidable tasks in physics. Yet in the face of this challenge, there's a quiet optimism. Various approaches, from loop quantum gravity to the holographic principle, offer glimpses of how quantum geometry might be described. Some suggest that space-time is built from discrete units, tiny atoms, of geometry that form a dynamic network. Others propose that space itself is an emergent property, a kind of collective illusion born from the entanglement of quantum information. Though these ideas remain speculative, they offer a vision of the universe that is both humbling and exhilarating. A world where geometry is not static but alive, where even emptiness is a seething, creative field. In this vision, the quantum nature of space-time is not a problem to be solved, but a mystery to be embraced. It reminds us that the universe is not a static collection of objects, but a dynamic interplay of relationships, a web of possibilities that is always in motion. The gentle undulations of space-time, the silent fluctuations of geometry, are not obstacles to understanding, but invitations to look deeper, to imagine a world where even the most basic concepts of distance and time are shaped by the quiet dance of the quantum. As we ponder these ideas, we are reminded that our familiar experiences of space and time are just one layer of a much richer reality. Beneath the surface, the quantum geometry of the universe flickers with possibility, each fluctuation a testament to the restless creativity of nature. In this quiet interplay, we find not just a scientific puzzle, but a reflection of our own curiosity. A reminder that in every question we ask about the universe, we are also asking about ourselves and our place within it. In the end, the quantum nature of space-time invites us to see the universe not as a finished picture, but as an ongoing conversation, a story written in the language of probability and geometry, of uncertainty and possibility. It is a story that continues to unfold with each new observation, each new idea, and each new step into the unknown. In this story, we find a profound beauty, a beauty that comes not from perfect answers, but from the endless curiosity that drives us to ask the next question and to look a little further beyond the horizon of what we know. Chapter 3. Quantum corrections to gravity. One of the most compelling aspects of modern physics is the recognition that our classical theories, as successful as they are at describing macroscopic phenomena, require corrections when quantum effects are taken into account. This is particularly true when it comes to gravity, a force that has long been understood through the elegant geometry of general relativity, but which, at its core, must also respond to the uncertainties and fluctuations inherent in the quantum world. The study of quantum corrections to gravity represents a profound attempt to bridge these two descriptions, revealing a universe that is not static and unchanging, but dynamic and alive with quantum motion. The starting point for understanding quantum corrections to gravity lies in the realization that, while general relativity provides an exceptionally accurate description of gravitational interactions at large scales, it is an incomplete story at very small distances or very high energies. In the classical picture, the curvature of space-time is determined solely by the distribution of mass and energy, with no room for the quantum uncertainties that define the behavior of particles and fields. Yet the universe itself is built from these quantum constituents, and so it is only natural to expect that gravity too must be shaped by the delicate interplay of quantum effects. At the heart of these quantum corrections is the concept of vacuum polarization, a phenomenon well studied in the context of quantum electrodynamics. In that domain, the vacuum is not empty, but teems with virtual particles that flicker in and out of existence. temporarily screening or enhancing the charges of the particles involved. When applied to gravity, this idea suggests that even the gravitational field is influenced by a sea of virtual gravitons and other quantum fluctuations that subtly alter its behavior. These corrections are typically so small that they are imperceptible in everyday experience, but they are essential for complete and consistent description of nature. The mathematical formalism that captures these corrections is typically framed in the language of effective field theories. In this approach, we acknowledge that our low-energy theories, like general relativity, are approximations that hold only within certain energy ranges. Quantum corrections appear as higher-order terms in the action, suppressed by factors related to the Planck scale but nonetheless present and calculable. These terms modify the classical equations of motion, introducing tiny deviations that could, in principle, become significant in extreme environments. One of the most fascinating consequences of these corrections is the prediction of phenomena that have no counterpart in classical general relativity. For example, quantum corrections can lead to the emergence of repulsive gravitational effects at very short distances, an idea that challenges our traditional understanding of gravity as a purely attractive force. These repulsive effects could play a crucial role in preventing the formation of singularities or in shaping the ultimate fate of collapsing matter. They suggest that deep within the heart of a black hole or in the early universe, gravity might behave in unexpected ways that soften the otherwise infinite densities predicted by classical theory. Another aspect of quantum corrections to gravity involves the running of gravitational coupling constants, analogous to the running of the fine structure constant in quantum electrodynamics. In this picture, the strength of gravity itself may depend on the energy scale at which it is probed, becoming weaker or stronger as one delves into the quantum regime. This running could have profound implications for the behavior of gravity at the highest energies, potentially smoothing out the singularities that plague classical descriptions and offering a natural mechanism for the resolution of these cosmic puzzles. Despite the elegance of these theoretical ideas, detecting quantum corrections to gravity remains a formidable challenge. The corrections are typically so small that they elude direct measurement in any current laboratory experiment. However, they could leave subtle imprints in cosmological observations, such as the spectrum of primordial gravitational waves or the distribution of matter in the early universe. Researchers are actively seeking these fingerprints, hoping that they will provide indirect evidence of the quantum corrections that shape the gravitational field. In this quest, black holes serve as natural laboratories where quantum corrections to gravity might reveal themselves. The intense gravitational fields near black hole horizons push classical general relativity to its limits, creating conditions where quantum effects are no longer negligible. Studies of Hawking radiation, for instance, already hint at the need for quantum corrections, as the evaporation of black holes cannot be fully explained within a purely classical framework. These hints encourage the search for a deeper understanding of how quantum mechanics modifies gravity in the most extreme environments. The interplay between quantum mechanics and gravity also raises intriguing questions about the very structure of space-time. If quantum corrections can smooth out the singularities predicted by general relativity, they might also offer clues about the initial state of the universe and the fate of information swallowed by black holes. Some proposals suggest that quantum corrections lead to a bounce at the center of a black hole, turning what would have been a singularity into a bridge to another region of space-time. Others propose that quantum corrections preserve information, avoiding the paradoxes that have long haunted our attempts to reconcile quantum mechanics with the classical geometry of space-time. These ideas remain speculative, but they highlight the rich interplay between quantum theory and gravity. They suggest that the universe is not a static stage, but a dynamic interplay of forces and fluctuations, where even the geometry of space-time is alive with quantum possibilities. This vision challenges our deepest assumptions and invites us to explore a world where the familiar rules of distance and time are shaped by the restless dance of quantum corrections. The search for quantum corrections to gravity is not merely an academic exercise. It speaks to the deep unity of the forces of nature and the desire to see gravity join its quantum cousins in a single coherent framework. It challenges us to rethink the nature of space-time itself, to imagine a world where geometry is not fixed but fluctuates in response to the quantum undercurrents that pervade all of existence. In this vision, the universe becomes a dynamic tapestry, its patterns shaped by the delicate interplay of quantum and classical effects. As we continue to explore these ideas, we are reminded that the path to a quantum theory of gravity is not a straight line, but a winding journey through some of the most subtle and beautiful concepts in physics. Each step brings us closer to a deeper understanding of the cosmos, weaving together the threads of general relativity and quantum mechanics into a single, unified story. In the quiet equations that describe these quantum corrections, we catch a glimpse of a universe that is both familiar and profoundly mysterious. In the end, the study of quantum corrections to gravity is a testament to the power of human curiosity and imagination. It reminds us that even the most fundamental aspects of reality, the geometry of space and the pull of gravity, are not beyond the reach of quantum fluctuations. They, too, are part of a world that is alive with possibility, a world that invites us to look deeper, to question more boldly, and to embrace the mysteries that lie at the heart of existence. In this quiet interplay of quantum corrections and gravitational geometry, we find not only the seeds of a new physics, but a reflection of our own restless quest to understand the universe in all its wonder and complexity. Chapter 4: Effective Field Theories and Gravity. In the search for a quantum understanding of gravity, effective field theories have emerged as one of the most practical and insightful approaches. While the idea of a complete unified theory that works at all scales remains a distant goal, effective field theories offer a way to capture quantum corrections to gravity within a well-defined and reliable framework. They allow physicists to focus on what can be measured and predicted within a certain range of energies, without being forced to confront the full complexity of quantum gravity all at once. The concept of an effective field theory is rooted in the observation that physical phenomena at different scales can often be described independently, with higher energy effects contributing small corrections to the behavior of low-energy processes. In this way, the theory serves as a bridge between the known and the unknown, providing accurate predictions in a domain where experiments can test them. The power of this approach lies in its humility. It does not claim to be a final theory of nature, but it gives a practical framework for organizing what is known and for systematically improving our understanding in manageable steps. When applied to gravity, effective field theories treat general relativity as a low-energy approximation to a more complete quantum theory that remains out of reach. In this view, the familiar equations of general relativity are just the first terms in a long expansion, with additional terms representing quantum corrections that become significant only at very high energies or very short distances. These corrections can be systematically organized using a method known as a derivative expansion, in which increasingly complex terms involving more derivatives of the fields are included to capture ever finer details of the quantum effects. This expansion reflects the fact that at low energies or in weak gravitational fields, the classical predictions of general relativity remain incredibly accurate. It is only when we probe closer to the Planck scale, where the energies involved become so large that quantum fluctuations of space-time itself can no longer be ignored, that the higher-order terms start to matter. In practical terms, this means that for most astrophysical and cosmological phenomena we observe, the corrections are vanishingly small, allowing general relativity to retain its predictive power. But for understanding the extreme conditions near black holes, the early universe, or the fundamental structure of space-time, these corrections become a window into the quantum world. The beauty of effective field theory is that it provides a systematic way to calculate these corrections without requiring a complete knowledge of the ultimate theory of quantum gravity. Instead of trying to solve the entire puzzle at once, physicists can focus on the pieces they can see and measure, using the known symmetries and structure of general relativity to guide the construction of the expansion. The result is a framework that is both flexible and predictive, capable of incorporating quantum effects in a controlled and systematic way. One of the remarkable features of this approach is that it treats gravity much like any other force of nature, at least within its domain of applicability. In the same way that quantum electrodynamics describes the interactions of charged particles through the exchange of photons, effective field theories of gravity can describe the interactions of massive objects through the exchange of gravitons, the hypothetical quanta of the gravitational field. These gravitons are not directly observable in any current experiment, but they provide a conceptual tool for understanding how quantum fluctuations of the gravitational field might influence the motion of matter and the shape of space-time itself. The calculations themselves are intricate and challenging, involving a careful accounting of how quantum fields interact with the curved geometry of space-time. But the underlying idea is simple. At each energy scale, only a limited set of interactions matter, with the most important contributions coming from the lowest order terms in the expansion. As one moves to higher energies, new terms become relevant, encoding the influence of physics that lies beyond the current theory. This hierarchy of scales is what makes effective field theory so powerful. It allows physicists to capture the essential features of quantum corrections without getting lost in the overwhelming complexity of a complete theory. In this way, effective field theories provide a kind of map for exploring the quantum corrections to gravity, showing where the classical description begins to break down and where new phenomena might emerge. They give physicists a set of tools to probe the subtle interplay between quantum uncertainty and gravitational geometry, tools that can be used to explore everything from the behavior of black holes to the earliest moments of the universe's history. The predictive power of effective field theories is one of their most compelling features. Even though the ultimate quantum theory of gravity remains elusive, the corrections calculated within this framework can be tested in principle, offering a window into the interplay of the known and the unknown. Observations of gravitational waves, the motion of compact objects, or the fine details of cosmological structure could, in the future, reveal the fingerprints of these quantum corrections, confirming the insights that effective field theory provides. At the same time, the limitations of this method are also a reminder of the challenges that lie ahead. Effective field theories are, by their nature, approximations that rely on a clear separation of scales. They work best when there is a large gap between the energies we can probe and the energies where the ultimate theory takes over. In the case of gravity, this gap is enormous, with the Planck scale lying far beyond the reach of any current or foreseeable experiment. This means that, while effective field theories give us a powerful tool for understanding quantum corrections, they are not the final word on the quantum nature of gravity. Yet even within these limitations, the insights gained are profound. They show that gravity, like all other forces, is shaped by the quantum fluctuations that pervade the vacuum, that the smooth geometry of space-time is only an approximation that holds within certain limits. They reveal that the search for quantum gravity is not about replacing general relativity, but about understanding the corrections that emerge when quantum mechanics is taken seriously at all scales. As we ponder these ideas, we are reminded that the universe is a tapestry woven from many threads, each one contributing to the pattern we see. Effective field theories are one of the most powerful tools we have for teasing apart these threads, for seeing how the familiar structures of general relativity emerge from the deeper, more mysterious quantum domain. They invite us to look beyond the apparent smoothness of space and time, to imagine a world where geometry itself is alive with quantum motion. In this quiet interplay of scales and corrections, we find a new kind of beauty, a beauty that comes not from perfect knowledge, but from the ability to see further than we could before, to glimpse the outlines of a deeper truth that lies just beyond the reach of our current understanding. It is a beauty that arises from the recognition that even our most cherished theories are approximations, that the story of the universe is always richer and more complex than any single equation can capture. As we move forward, guided by the principles of effective field theory, we carry with us not just the equations and calculations, but a philosophy of humility and curiosity. It is a philosophy that values precision and approximation in equal measure, that sees the limits of our knowledge not as barriers, but as invitations to explore further. And in that spirit of exploration, we find hope that each correction, each subtle adjustment to our understanding brings us one step closer to the ultimate picture of the quantum universe. Chapter 5. Loop Quantum Gravity, Discrete Spacetime. In the quiet revolution of modern physics, one of the most intriguing proposals to reconcile quantum mechanics with gravity is the theory known as loop quantum gravity. Unlike some approaches that seek to unify all forces or introduce additional dimensions, loop quantum gravity takes a direct path. It focuses solely on gravity, seeking to quantize the very geometry of spacetime itself. It represents a bold attempt to describe the universe as woven from loops of quantum geometry, challenging our traditional notions of space and time, and offering a radical reimagining of the very stage on which all of physics unfolds. The origins of loop quantum gravity can be traced back to the realization that classical general relativity, for all its elegance, cannot fully capture the behavior of space-time at the Planck scale. The continuous fabric of general relativity must somehow be compatible with the discrete, probabilistic world of quantum mechanics. Loop quantum gravity arose as an effort to take this challenge seriously, treating gravity not as a force to be mediated by a new particle, but as a manifestation of the dynamic geometry of spacetime itself. It builds upon the fundamental insight that geometry is not just a passive backdrop, but an active participant in the cosmos. At the heart of loop quantum gravity lies the idea that space is not continuous, but composed of tiny, discrete chunks or quanta. These quanta of geometry are represented by mathematical structures called spin networks, which provide a kind of scaffold for the quantum geometry of space. In this view, the smooth curves and surfaces of classical geometry emerge only as an approximation to the collective behavior of these networks at scales much larger than the Planck length. Each intersection, each link in this network, represents a quantum of area or volume, a minimal unit of spatial measurement that cannot be divided further. This discrete nature of space-time has far-reaching consequences. In the loop quantum gravity framework, areas and volumes are quantized, meaning they can take on only certain discrete values. There is no meaning to a distance shorter than the Planck length. no measurement of area smaller than the quantum of area defined by these networks. This granular structure of geometry is not an artifact of our ignorance, but a fundamental feature of the universe at the deepest level. It suggests that the apparent smoothness of space that we observe is a kind of large-scale illusion, a statistical average of countless quantum grains of geometry that individually flicker in and out of existence. One of the most compelling features of loop quantum gravity is how it modifies our understanding of space and time. In classical physics, we treat space and time as a continuum, a backdrop for the motion of objects and the evolution of fields. But loop quantum gravity teaches us that this continuum is an emergent phenomenon, a statistical smoothing out of the tiny, discrete building blocks that truly define the universe. Time itself is seen not as a flowing river, but as an ordering of events, a sequence of quantum transitions between spin network states. This radical perspective challenges us to imagine a world where the very notion of time is woven from the relationships between these quantum grains of geometry. The mathematical tools that underlie loop quantum gravity are intricate and abstract, drawing on techniques from gauge theory and differential geometry. Instead of working with the familiar metric of general relativity, loop quantum gravity reformulates the theory in terms of connections and holonomies, concepts borrowed from the study of fiber bundles and gauge fields. These variables capture the gravitational field not as a smooth surface, but as a network of interactions that loop around one another, encoding the twisting and weaving of geometry itself. A central insight of loop quantum gravity is that these loops are not arbitrary, they are quantized themselves, carrying discrete units of area and volume. These loops can be visualized as tiny threads that stitch together to form a vast cosmic fabric, a web of geometry that is always in flux, always alive with quantum possibilities. At larger scales, this network of loops averages out to the familiar geometry of space-time, explaining why classical general relativity works so well in the world we see every day. But deep down, at the smallest scales, space is not a continuous canvas, but a shimmering sea of loops and links, a dynamic tapestry of quantum geometry. One of the profound implications of this approach is that it removes the singularities that plague classical general relativity. In the loop quantum gravity picture, the infinite curvatures of black hole cores, or the Big Bang, are replaced by regions of extremely high but finite curvature. The quantization of geometry prevents the collapse into a true singularity, suggesting that space-time can be extended beyond these points in ways that classical theory cannot describe. This hints at a possible resolution to some of the deepest puzzles of cosmology, including the fate of information in black holes and the true nature of the beginning of the universe. Loop quantum gravity does not attempt to unify gravity with the other fundamental forces directly, focusing instead on building a consistent quantum description of gravity alone. Yet even in this narrower scope, it has revealed deep connections to other areas of physics, from the mathematics of knots and braids to the study of quantum information. The spin networks that define loop quantum geometry resemble the diagrams used in topological quantum field theory, suggesting that at the deepest level, space and information might be two sides of the same coin. The philosophical implications of loop quantum gravity are as profound as its technical challenges. It asks us to abandon the comforting image of a smooth, continuous space in favor of a world where geometry itself is granular and dynamic. It suggests that the flow of time is not an absolute feature of the universe, but a reflection of the relationships between the quanta of geometry. It calls us to imagine a cosmos where the fabric of reality is woven from loops and nodes, where the apparent stability of the world is an emergent feature of a restless quantum sea. As we explore these ideas, we are drawn into a vision of the universe that is at once familiar and alien, The familiar curves of gravity and the passage of time are still there, but beneath them lies a quantum dance of loops and connections that defies our classical intuitions. It is a vision that challenges us to think differently, to see the universe not as a fixed stage, but as a living network of relationships that gives rise to everything we see. The journey to fully understand loop quantum gravity is far from complete. The mathematics is challenging. The experiments needed to test its predictions are beyond our current reach, and the conceptual shifts it demands are profound. Yet in these very challenges lies a kind of hope. A hope that by embracing the granular, discrete nature of space-time, we may find a path to a deeper unity of the cosmos. Loop quantum gravity invites us to listen more closely to the subtle whispers of the quantum world, to imagine that even the void is alive with structure and possibility. It reminds us that the universe is more than what we see, that beneath the smooth flow of time and the gentle pull of gravity lies a tapestry of loops and links, forever weaving the story of existence. In the quiet elegance of loop quantum gravity, we glimpse a world where geometry itself becomes a quantum phenomenon, a restless interplay of possibility and form. We are invited to look beyond the familiar, to see the universe as a dynamic web of interactions, where even the most basic concepts of distance and duration are shaped by the delicate structure of quantum loops. In this dance of loops and nodes, we find not only a new way of understanding gravity, but a new way of understanding ourselves, as creatures woven into the very geometry of the cosmos. Chapter 6. String Theory: Gravity from Vibrating Strings. In the vast landscape of modern theoretical physics, string theory stands as a bold and ambitious framework that seeks to unify all known forces of nature, including gravity, into a single quantum description. Unlike traditional approaches that treat particles as point-like entities, string theory proposes that the fundamental building blocks of reality are tiny, vibrating strings. Each mode of vibration of these strings corresponds to a different particle, and in this harmonious framework, gravity emerges not as a separate force but as a natural consequence of the string's dynamics. The origin of string theory can be traced back to the attempts to understand the strong nuclear force in the late 20th century. It soon became apparent, however, that the mathematical structure of the theory had implications far beyond the realm of nuclear interactions. The realization that string theory naturally includes a massless spin-2 particle, which could be interpreted as the graviton, the quantum carrier of gravity, was a turning point. This discovery suggested that gravity itself emerges from the deep mathematical framework of string vibrations, offering a new way to think about one of the oldest forces in nature. One of the most remarkable aspects of string theory is its ability to weave together forces that appear so different in our everyday experience. Electromagnetism, the strong and weak nuclear forces, and gravity all emerge from the different vibrational modes of strings, each with its own unique signature. In this picture, the particles that make up the world around us are not indivisible points, but tiny loops or segments of string, each carrying the unique imprint of its vibrational state. This idea unites the diverse phenomena of the universe into a single, elegant language of oscillation and resonance. The mathematical structure of string theory is both elegant and formidable. It requires the introduction of additional spatial dimensions beyond the familiar three of our everyday lives. These extra dimensions are thought to be compactified or curled up at scales so small that they remain hidden from direct observation, their presence felt only through the subtle effects they have on the vibrational patterns of strings. The geometry and topology of these hidden dimensions play a crucial role in determining the physical properties of the particles that emerge from the theory, linking the very shape of the cosmos to the behavior of matter and energy. This idea that gravity is not a separate force, but an emergent property of string vibrations, challenges our most basic intuitions about the nature of reality. It suggests that the familiar curvature of space-time, which we experience as gravity, is a large-scale consequence of the underlying quantum dance of strings. In this vision, geometry itself is not a fixed backdrop, but an ever-changing tapestry woven from the vibrations of these tiny filaments. Matter and space-time become two sides of the same fundamental process, blurring the boundary between what we once thought of as separate realms. The promise of string theory extends beyond a mere unification of known forces. It provides a framework for exploring phenomena that lie far beyond the reach of current experiments, including the behavior of black holes and the possible structure of the early universe. String theory has inspired new ways of thinking about the nature of singularities, the fate of information in black holes, and even the possibility of multiple universes connected through hidden dimensions. In this sense, it is not merely a theory of particles and forces, but a sweeping narrative about the deepest structures of the cosmos. One of the striking features of string theory is the remarkable consistency it requires. The mathematical conditions for the theory to be free of contradictions are so restrictive that they not only demand the presence of extra dimensions, but also determine many of the features of the interactions it describes. This rigidity is both a challenge and a guiding light, suggesting that string theory is more than just an arbitrary construction. It may be the only framework that can consistently combine gravity with the principles of quantum mechanics. Yet this very rigidity also gives rise to one of the most profound puzzles in string theory, the so-called landscape problem. String theory does not produce a single unique description of the universe, but instead allows for a vast number of possible vacuum states, each corresponding to a different compactification of the extra dimensions. This landscape of solutions is so vast that it has led to the idea that our universe might be just one of many, each with its own physical laws and constants. This perspective resonates with the concept of a multiverse, a dizzying vista of possibilities that stretches the imagination and challenges our traditional notions of uniqueness and determinism. Despite the elegance and promise of string theory, it remains a theory without direct experimental confirmation. The energy scales at which its distinctive predictions would become apparent are far beyond the reach of any current or foreseeable collider or telescope. However, string theory has had a profound impact on theoretical physics, offering insights that extend beyond its immediate predictions. It has deepened our understanding of dualities, correspondences between seemingly different physical descriptions, hinting at a hidden unity that runs through the tapestry of physical law. The interplay between string theory and gravity is particularly rich in the study of black holes. String theory has provided compelling explanations for the entropy of black holes, linking it to the microscopic degrees of freedom of strings and extended objects called brains. This perspective provides a statistical foundation for black hole thermodynamics, offering a glimpse into the quantum underpinnings of space-time's most extreme environments. In this way, string theory has turned black holes from enigmatic endpoints into fertile grounds for exploring the marriage of gravity and quantum mechanics. Beyond black holes, string theory has reshaped our understanding of the early universe. In scenarios such as brain inflation, the motion of higher dimensional membranes within the extra-dimensional space can drive rapid expansion, offering potential explanations for the observed smoothness and flatness of the cosmos. These ideas blend geometry, quantum mechanics, and cosmology in a single narrative, weaving a story of creation that is as breathtaking as it is mathematically rigorous. Philosophically, string theory invites us to rethink what it means for something to be fundamental. In a world built from vibrating strings, The solidity of matter dissolves into patterns of energy and geometry, an endless dance of oscillation that underlies all that we see. It suggests that the universe is not a static collection of objects, but a dynamic symphony where each note contributes to the whole, and where gravity itself emerges from the subtle interplay of quantum vibrations. As researchers continue to refine the mathematical structures of string theory and search for ways to connect its insights to observable phenomena, the journey is one of both challenge and wonder. String theory's promise is not just a final answer to the question of quantum gravity, but a new way of seeing the universe, a way that reveals the deep interconnectedness of space, time, and matter. It invites us to imagine that everything we see is a fleeting resonance, a momentary harmony in the endless music of the cosmos. In the quiet elegance of vibrating strings, we glimpse a universe that is both mysterious and deeply connected. Gravity is not an external force imposed upon matter, but a natural outgrowth of the cosmic symphony, a melody that shapes the dance of galaxies and the flickering of quantum fields. This perspective reminds us that the search for quantum gravity is not just about equations and measurements. It is about understanding the profound unity of everything that exists, and in that understanding, finding a reflection of our own search for meaning and coherence in the universe. Chapter 7: Black Hole Thermodynamics and Quantum Gravity. In the world of modern physics, few objects capture the imagination and challenge our understanding of nature quite like black holes. They are regions where gravity becomes so intense that nothing, not even light, can escape. Their existence was once considered a curious prediction of general relativity, but over the past few decades, they have transformed into a focal point for exploring the interplay between gravity and quantum mechanics. At the heart of this exploration lies the rich and surprising field of black hole thermodynamics, a set of ideas that suggest black holes are not merely cosmic sinkholes, but objects with deep thermodynamic properties. This intersection of gravity, quantum theory, and thermodynamics provides one of the most compelling windows into the mysteries of quantum gravity. The first hints of a thermodynamic character to black holes emerged in the early 1970s, when physicists began to notice that black holes seemed to obey a set of laws reminiscent of the laws of thermodynamics. Just as ordinary systems have entropy and temperature, black holes appeared to exhibit analogous properties. This was a startling realization. After all, black holes were thought to be featureless, defined only by mass, charge, and spin, a concept known as the no-hair theorem. How could such seemingly simple objects possess something as subtle and statistical as entropy? The answer began to take shape with the work of Jacob Bekenstein, who proposed that the area of a black hole's event horizon, a boundary beyond which nothing can return, could be associated with entropy. He suggested that as matter falls into a black hole, the information it carries is not destroyed, but somehow encoded in the geometry of the event horizon. This insight was revolutionary, hinting at a deep link between gravity and information, and laying the groundwork for what would become a rich and vibrant area of theoretical physics. Stephen Hawking took these ideas a step further when he discovered that black holes are not entirely black. In a stunning calculation, he showed that quantum effects near the event horizon allow black holes to emit radiation, a phenomenon now known as Hawking radiation. This radiation is thermal, with a temperature that depends on the black hole's mass. The smaller the black hole, the hotter it becomes. In one stroke, this result connected the geometry of space-time with the laws of quantum field theory and thermodynamics, showing that black holes radiate and eventually evaporate, losing mass over time. Hawking's discovery had profound implications. It meant that black holes have a temperature and, by extension, an entropy that grows with the area of the event horizon. This entropy is enormous compared to that of ordinary matter, reflecting the immense number of microscopic states that could be hidden behind the horizon. The entropy of a black hole is proportional to the area of its event horizon in Planck units, a relationship known as the Bekenstein-Hawking formula. This formula suggests that the information content of a black hole is not stored in its volume, as one might expect, but in its surface area. This peculiar result hints at a holographic nature of space-time, where the fundamental degrees of freedom of a region might reside on its boundary. The thermodynamic properties of black holes force us to confront some of the most profound questions in physics. If black holes can evaporate through Hawking radiation, what happens to the information carried by the matter that fell in? In classical general relativity, information about the initial state of matter that formed the black hole seems to be lost once it crosses the event horizon. But quantum mechanics insists that information cannot be destroyed. This apparent conflict is known as the black hole information paradox, a puzzle that has driven decades of research and speculation. One possible resolution to the paradox lies in the idea that the information is not truly lost, but is encoded in subtle correlations within the Hawking radiation. This possibility suggests that the radiation is not perfectly thermal, but carries tiny imprints of the black hole's history, a delicate fingerprint of quantum entanglement that might preserve the information in a highly scrambled form. Others propose that the very nature of the black hole interior is different from what classical relativity predicts, that quantum gravity modifies the space-time near the horizon in ways that allow information to leak out. The study of black hole thermodynamics has become a testing ground for these ideas, a place where the principles of quantum theory, thermodynamics, and gravity collide and reveal their underlying connections. It has inspired new approaches to quantum gravity, from string theory's description of black hole microstates to the proposal that black holes are fundamentally quantum objects, with horizons that are more like dynamic membranes than static surfaces. One of the most remarkable aspects of this field is the universality of the laws it uncovers. The four laws of black hole mechanics, analogous to the laws of thermodynamics, apply regardless of the details of the black hole's composition. They reveal that black holes are not merely curiosities of Einstein's equations, but objects with deep thermodynamic structure, shaped by quantum effects that we are only beginning to understand. In these laws, we see the unity of the physical world, where gravity and quantum mechanics speak the same language through the shared vocabulary of entropy, temperature, and energy flow. Black hole thermodynamics also invites us to rethink the meaning of space-time itself. If the entropy of a black hole is proportional to its area rather than its volume, it suggests that the fundamental degrees of freedom of space-time may not be spread out through the entire volume, but confined to lower dimensional boundaries. This idea resonates with the holographic principle, a bold conjecture that the information contained in a region of space can be fully described by a theory living on its boundary. Such a perspective challenges our classical notions of locality and dimensionality, hinting at a universe where gravity and quantum mechanics merge into a more subtle and intricate structure. The implications of these insights extend far beyond black holes themselves. They offer clues to the quantum structure of space-time, to the nature of the vacuum, and to the fate of the universe in its earliest moments. Black hole thermodynamics has become a cornerstone for many approaches to quantum gravity, a beacon guiding us through the fog of incomplete theories toward a more complete picture of how the universe truly works. The journey to fully understand the thermodynamic properties of black holes is far from over. Experimental confirmation of Hawking radiation remains elusive, as the temperature of astrophysical black holes is far too low to detect directly. However, Analog models in condensed matter systems have provided tantalizing glimpses of similar phenomena, suggesting that the principles underlying black hole thermodynamics might be more universal than we imagined. As we reflect on these ideas, we are drawn into a vision of the cosmos that is at once humbling and exhilarating. Black holes, once thought to be cosmic tombs, emerge as dynamic objects that blend the mysteries of gravity and quantum theory into a single, shimmering tapestry. They remind us that even the most extreme corners of the universe are governed by the same gentle principles that shape the world around us. Principles of balance, of flow, and of the ceaseless interplay between matter, energy, and information. In the quiet whispers of black hole radiation, we hear the echoes of the deepest truths of the cosmos. In the subtle warmth of their thermal glow, we catch a glimpse of a world where gravity and quantum mechanics are not separate domains, but two aspects of a single, unified reality. This vision invites us to look deeper, to imagine that beyond the event horizon of our knowledge lies a landscape where the fabric of space-time itself is alive with quantum possibility. Black hole thermodynamics teaches us that the universe is not static but dynamic, not an inert backdrop, but a living tapestry of energy and form. It shows us that even in the cold darkness of a black hole, there is warmth and movement, a faint shimmer of quantum activity that speaks to the boundless creativity of the cosmos. In this delicate interplay of gravity and quantum fields, we find a profound reminder of our own quest for understanding, a quest that continues to drive us forward, ever deeper into the mysteries of existence. In this vision, black holes become more than just regions of no return. They become gateways to new ways of thinking, laboratories for the deepest ideas in physics, and quiet beacons that illuminate the path toward a quantum theory of gravity. They challenge us to see the universe not as a collection of separate parts, but as a single, interconnected whole, where even the darkest mysteries are woven from the same bright threads of possibility and wonder. Chapter 8: Holographic Principle and Quantum Gravity. In the unfolding story of modern physics, the holographic principle has emerged as one of the most provocative and transformative ideas about the nature of reality. It suggests that everything we experience in the universe, every event, every fluctuation of matter and energy, might be described not by the three-dimensional volume we inhabit, but by information encoded on a lower dimensional boundary. This startling proposition redefines our understanding of space, time, and gravity, and offers a powerful glimpse into the quantum structure of the cosmos. At its core, the holographic principle challenges us to see the universe in a radically new way, one that blends geometry, quantum theory, and the flow of information into a seamless, interconnected tapestry. The inspiration for the holographic principle can be traced to the study of black holes. Physicists found that the entropy of a black hole, a measure of the information it can contain, does not scale with its volume as one might expect. Instead, it grows in proportion to the area of its event horizon. This unexpected result, first glimpsed through the pioneering work of Bekenstein and Hawking, hinted at a deep and mysterious connection between information and geometry. If the entropy, and therefore the information content, of a black hole depends only on the area of its surface, could this be a clue to a broader principle about the universe itself? The idea that the universe might be holographic in nature was given voice by physicist Gerard Hooft, and later developed by Leonard Susskind, who proposed that the entire universe could be described by a theory defined on its boundary. In this view, the three-dimensional world we perceive is an emergent phenomenon, a projection of more fundamental information stored on a distant horizon. It is as if the richness of our reality, the colors, sounds, and textures of experience, arises from a cosmic film imprinted on a vast, invisible screen. What makes this idea so compelling is its ability to resolve puzzles that arise when trying to merge quantum mechanics with gravity. In classical physics, space and time are continuous, smooth, and filled with an infinite number of points. But quantum mechanics teaches us that information is finite and that the very act of observation is tied to discrete units of information. The holographic principle bridges these views by suggesting that the universe's most fundamental degrees of freedom are encoded on two-dimensional surfaces, creating a finite and consistent description of the world. At first glance, this notion seems almost magical, a conjuring trick where the familiar solidity of three dimensions emerges from a lower dimensional foundation. But it is rooted in rigorous mathematics and has found compelling realization in specific physical models. One of the most striking examples comes from the study of anti-de Sitter space, a kind of curved geometry that provides a simplified model of the cosmos. In this setting, the holographic principle becomes a precise statement known as the ds-CFT correspondence, which equates a theory of gravity in the bulk with a quantum field theory defined on the boundary. This duality has provided a powerful laboratory for testing ideas about quantum gravity, allowing physicists to explore how space-time itself might emerge from a more fundamental quantum theory. The implications of the holographic principle extend far beyond the confines of theoretical physics. It suggests that the geometry of the universe is not a fixed stage, but a dynamic consequence of quantum information. In this picture, gravity is not an external force, but an emergent property of how information is organized and entangled across space-time. The very curvature of the universe, the warping and flexing of space that guides the motion of stars and galaxies, might arise from the invisible threads of information that connect distant points in a cosmic web. This perspective challenges us to rethink what it means to exist in a three-dimensional world. If our familiar experience of up and down, of near and far, is a kind of projection, then the ultimate reality might be stranger and more subtle than anything we can directly perceive. The holographic principle invites us to consider that what we call space itself is not a container for matter, but a pattern woven from the correlations of quantum information. In this view, the smallest grains of geometry are not inert but alive with possibility, their arrangement shaping the flow of time and the structure of the cosmos. The power of the holographic principle lies not just in its mathematical elegance, but in its philosophical richness. It offers a vision of the universe where boundaries and surfaces become the seeds of reality, where what seems distant can be intimately connected through the hidden language of quantum entanglement. It suggests that the edge of a region holds the key to understanding its interior, that the horizon is more than a limit. It is a doorway to the deepest truths of the universe. As physicists explore the implications of the holographic principle, they are uncovering surprising connections between gravity, thermodynamics, and quantum information. Black holes, once thought of as cosmic sinkholes, become windows into the way information is stored and processed in the fabric of space-time. The entropy of a black hole becomes a measure of the possible configurations of quantum geometry on its horizon, revealing a hidden structure that speaks to the unity of matter and information. The idea that the universe itself might be holographic is not merely a poetic metaphor. It is a precise statement about how quantum gravity might work, a blueprint for reconciling the continuous geometry of general relativity with the discrete, probabilistic world of quantum theory. It suggests that the smoothness of space-time is an emergent phenomenon, a collective behavior of quantum degrees of freedom that encode information on lower dimensional surfaces. In this way, the holographic principle provides a conceptual bridge between the large and the small, the classical and the quantum. One of the most exciting aspects of the holographic principle is its potential to illuminate the nature of time. In classical physics, time is an ever-flowing river, a backdrop for change. But in the holographic view, time itself may be woven from the entanglement patterns of quantum information on a boundary. This hints at a world where time is not a fundamental ingredient, but an emergent property, a consequence of how information is stitched together at the edges of space. The exploration of the holographic principle has opened new avenues for understanding the cosmos. It has inspired ideas about the early universe, where quantum fluctuations on a primordial horizon might have seeded the structures we see today. It has offered new insights into the behavior of strongly interacting systems, where holographic dualities provide powerful tools for studying complex quantum phenomena. It has even suggested that space-time itself might be a kind of quantum error-correcting code, resilient to small perturbations and capable of preserving information in the face of chaos. In the quiet elegance of these ideas, we find a profound reminder of the universe's hidden unity. The holographic principle challenges us to look beyond the visible, to imagine that the world we experience is just one expression of a deeper, more subtle order. It invites us to see the universe not as a collection of separate parts, but as a single, interconnected whole, where every surface holds the key to understanding the vast interior it encloses. As we ponder the holographic principle, we are drawn into a vision of reality that is both humbling and inspiring. It suggests that the universe is a symphony of information, a dynamic interplay of patterns that give rise to the shapes and motions we see in the night sky. It teaches us that the boundaries we draw between inside and outside, between here and there, are not fixed but fluid, reflections of a deeper harmony that connects every point in space and every moment in time. In this vision, gravity itself becomes a whisper of quantum information, a gentle curve in the geometry of entanglement that binds the cosmos together. Space is no longer a passive stage but an active player, a living network that holds the memories of all that has ever happened. Time, too, becomes a tapestry of possibilities, a record of change encoded in the shimmering threads of quantum connections. In the end, the holographic principle is more than a theory. It is an invitation to wonder, a doorway to a new way of seeing the universe and our place within it. It calls us to embrace the mystery of a world where the edge is as rich as the center, where the boundary is the birthplace of all that is and all that can be. In that quiet invitation, we find not only the promise of a deeper physics, but a profound reflection of the boundless curiosity that drives us to explore, to question, and to dream of the infinite possibilities that lie just beyond the horizon of what we know. Chapter 9: Gravitons and Quantum Fluctuations. In the ongoing journey to understand gravity at the quantum level, one of the most captivating concepts is that of the graviton, a hypothetical quantum particle that would mediate the gravitational force in the same way that photons mediate electromagnetic interactions. While gravitons remain purely theoretical, their existence would represent a profound bridge between the well-established realm of quantum field theory and the geometric language of general relativity. In this chapter, we explore how gravitons emerge from the idea of quantized gravitational fields and how their interplay with quantum fluctuations might reveal the deepest secrets of the universe. The concept of the graviton arises naturally when we apply the principles of quantum field theory to the gravitational field. In quantum electrodynamics, the electromagnetic field is quantized, and photons appear as discrete packets of energy that carry the force between charged particles. By analogy, if the gravitational field is similarly quantized, it should also give rise to a particle, the graviton, that carries the force of gravity between masses. This particle would be massless, like the photon, and would have a spin of 2, reflecting the tensorial nature of the gravitational interaction. While the mathematics of gravitons is elegant, their direct detection is beyond the reach of current experiments. Gravitons would interact extremely weakly with matter, making them elusive messengers of the quantum nature of gravity. Yet, even without direct observation, the idea of the graviton provides a conceptual framework for understanding how gravity might fit into the quantum tapestry that weaves together all the forces of nature. At the heart of this quantum perspective lies the interplay between gravitons and quantum fluctuations. In the quantum world, the vacuum is not an empty void, but a restless sea of activity. Even in the absence of matter, quantum fields fluctuate, creating transient pairs of particles and antiparticles that momentarily exist before annihilating one another. These vacuum fluctuations are a fundamental feature of quantum theory, giving rise to observable effects such as the Casimir force and the Lamb shift in atomic spectra. If gravity is indeed a quantum field, it too must participate in this restless dance of fluctuations. The gravitational field would fluctuate in the same way as other quantum fields, with gravitons popping in and out of existence alongside their more familiar counterparts. These fluctuations would subtly influence the geometry of space-time, causing tiny ripples in the fabric of reality that, though imperceptible in daily life, might leave imprints in the cosmos on the grandest scales. One arena where the influence of gravitons and quantum fluctuations becomes especially significant is the early universe. In the moments after the Big Bang, the universe was a hot, dense soup of particles and energy, a seething cauldron of quantum fields in violent motion. During this epoch, the quantum fluctuations of all fields, including the gravitational field, would have played a crucial role in shaping the large-scale structure of the universe we see today. The tiny variations in density that seeded the formation of galaxies may well have their origins in these primordial quantum jitters. The idea that quantum fluctuations can influence cosmic structure is both humbling and awe-inspiring. It suggests that the vast tapestry of galaxies and clusters, the immense voids and filaments that stretch across billions of light years, is in some sense a fossil record of the quantum fluctuations that rippled through the newborn universe. In this vision, the graviton is more than a theoretical particle. It is a participant in the ongoing story of cosmic evolution, a silent witness to the interplay between the smallest and largest scales of reality. In addition to shaping cosmic structures, gravitons and quantum fluctuations may also offer insights into the fate of black holes. Near the event horizon of a black hole, the gravitational field is intense and curved, creating conditions where quantum fluctuations become significant. In this extreme environment, gravitons would contribute to the subtle interplay of forces that govern the behavior of the horizon. The study of these processes offers a window into the deep relationship between gravity and quantum mechanics, hinting at the ways that information and geometry are interwoven in the fabric of space-time. The challenge of incorporating gravitons into a consistent theory of quantum gravity is formidable. Unlike other quantum fields, gravity interacts with everything, including itself. This self-interaction makes the mathematics of quantum gravity particularly complex, giving rise to infinities and divergences that cannot be easily tamed by the standard techniques of renormalization. These difficulties highlight the need for new ideas and new mathematical frameworks that go beyond the traditional approaches of quantum field theory. Despite these challenges, the pursuit of a theory that includes gravitons remains one of the most active and inspiring areas of research in theoretical physics. Various approaches, from loop quantum gravity to string theory, seek to provide a consistent description of how gravitons and quantum fluctuations weave together the story of space-time. Each offers its own perspective on how the universe might be built from the quantum interplay of geometry and information, guiding us closer to a unified understanding of the cosmos. The implications of this quest extend beyond the confines of mathematics and physics. They touch on some of the deepest questions about the nature of reality. Is space-time itself a fundamental entity, or is it an emergent property of more basic quantum structures? Are the ripples of gravitons a reflection of an underlying sea of information, a holographic record of every event that has ever happened? These questions invite us to see gravity not just as a force, but as a window into the profound unity of the universe. As we explore these ideas, we are drawn into a vision of the cosmos that is both subtle and interconnected. The graviton becomes a symbol of the restless dynamism of the quantum world, a whisper of the fluctuations that underlie every corner of space and time. In the silent motion of these quantum ripples, we catch a glimpse of a universe that is alive with possibility, where every point in space is linked to every other through the invisible threads of quantum entanglement. This vision challenges us to rethink what it means to measure, to observe, and to understand. In the world of quantum gravity, the act of observation is not a passive process, but a dynamic interplay between the observer and the observed, a dance of probabilities and uncertainties that shapes the very fabric of reality. Gravitons and quantum fluctuations remind us that the universe is not a static stage, but an unfolding drama, a story written in the language of quanta and waves. The journey to understand gravitons is far from over. New experiments, new telescopes, and new mathematical tools continue to refine our picture of how quantum fluctuations shape the cosmos. As we listen for the faint echoes of gravitons in the ripples of space-time, we are reminded that the universe is richer and more mysterious than we have ever imagined. Each step brings us closer to a world where gravity and quantum mechanics are not separate domains, but two aspects of a single, unified story. In this story, the graviton is not merely a particle. It is a messenger of the deep unity that binds together all of existence, a signpost on the path to a quantum theory of gravity. It speaks to the boundless curiosity that drives us to explore the universe, to see beyond the horizon of what is known, and to embrace the mystery that lies at the heart of all things. In the quiet presence of gravitons and the ceaseless dance of quantum fluctuations, we find a reflection of the infinite potential of the cosmos and of ourselves as part of that grand and ever-unfolding adventure. Chapter 10: Observational Frontiers and Quantum Gravity Clues. As our understanding of the universe deepens, the tantalizing search for quantum gravity remains a quest that stretches the very boundaries of human curiosity. Despite the enormous theoretical progress made in understanding how quantum principles might shape gravity, direct observational evidence remains one of the most challenging frontiers in physics. In this chapter, we journey through the subtle yet promising clues that the universe offers, clues scattered across the cosmic landscape, hidden in the shimmering patterns of ancient light, or lurking in the depths of the most powerful gravitational wells. At first glance, the domain of quantum gravity seems remote from our everyday experience. After all, the quantum realm typically reveals itself at scales far smaller than those we can directly access, while gravity rules the large, majestic structures of the cosmos. Yet nature has a way of bridging these scales, leaving faint signatures of the smallest processes in the largest structures. Our challenge lies in deciphering these subtle imprints, in reading the quiet messages encoded in the universe's grand design. One of the most promising arenas for finding these clues is the early universe. In the moments after the Big Bang, the universe was a cauldron of seething energy, a realm where quantum fluctuations and gravitational dynamics danced together in ways that shaped everything we see today. As the universe expanded and cooled, the quantum seeds of density variations left their mark on the distribution of galaxies and the cosmic web that binds them. These patterns, imprinted in the faint glow of the cosmic microwave background, offer a kind of fossil record of the quantum gravity processes that operated in those earliest moments. Observatories that map the cosmic microwave background have given us a remarkably detailed portrait of the infant cosmos. Tiny variations in temperature, measured with exquisite precision, trace the imprints of those early quantum fluctuations. Though these patterns are usually analyzed within the framework of classical cosmology, there's a growing recognition that they might contain faint echoes of quantum gravitational effects, whispers of a time when the geometry of space-time itself was uncertain and fluctuating. Beyond the early universe, black holes offer another window into the quantum gravity frontier. The intense gravitational fields near a black hole's event horizon create conditions where quantum and gravitational effects converge. Observations of black hole mergers, captured in the faint but unmistakable ripples of gravitational waves, have already begun to reveal the dynamism of space-time in these extreme environments. As gravitational wave detectors become more sensitive, they might detect tiny deviations from classical predictions, subtle hints of quantum corrections that could point the way to a deeper theory. The detection of gravitational waves themselves stands as a triumph of human ingenuity and as a gateway to this new frontier. Each wave carries with it a story written in the language of gravity, the spiraling dance of merging black holes, the moment of collision, and the final ringing of the merged remnant. Yet beneath these dramatic events, there may be quiet signatures of quantum gravity, faint modulations in the waves, deviations so slight that they demand the most precise instruments to reveal. Other possible clues lie in the behavior of high-energy particles that travel across the vast distances of space. Cosmic rays, those messengers from the depths of the cosmos, could carry imprints of quantum gravity if the structure of space-time at the smallest scales affects how they propagate. The possibility that space-time itself might behave like a kind of quantum foam, a restless sea of fluctuations, could lead to tiny changes in the arrival times of these particles, subtle shifts in the energy they lose as they cross the cosmos. Searching for these effects is no easy task. The universe is filled with noise, astrophysical processes that can mimic or obscure the delicate signals of quantum gravity. Disentangling these threads requires careful observation, clever techniques, and above all, patience. It is the work of decades and generations, a testament to the quiet determination of those who seek to lift the veil on the deepest structures of reality. One of the most promising frontiers in this search is the study of light from distant sources. Gamma-ray bursts, those brief yet powerful flashes of energy from cataclysmic events billions of light-years away, travel through the cosmic expanse, crossing regions where quantum gravity effects might subtly accumulate. Some models suggest that the very speed of light might depend, in a minuscule way, on its energy, an idea known as Lorentz invariance violation. Observing or constraining such effects would be a profound step toward testing the fingerprints of quantum gravity in the laboratory of the cosmos. These searches are not merely academic. They represent a dialogue between theory and observation, a conversation that stretches across the vastness of space and the depths of mathematical abstraction. They remind us that even the most speculative theories must ultimately face the quiet judgment of the sky. In every observation, in every photon or gravitational wave that reaches us, there is a chance to catch a glimpse of the quantum structure of space-time, a fleeting view of the quantum threads that weave the tapestry of the cosmos. As we refine our instruments and extend our reach, new windows continue to open. The next generation of gravitational wave detectors promises to reveal mergers with unprecedented precision, perhaps even capturing the subtle echoes of quantum corrections. Telescopes that peer deeper into the cosmic microwave background, that measure its polarization and faint distortions, might uncover hints of primordial gravitational waves. whispers from a time when quantum gravity ruled the universe. Even as we search for these direct clues, there is another frontier that is no less important: the interplay of observation and theory. Quantum gravity is not a single theory, but a family of ideas, each offering a different perspective on how the smooth fabric of space-time emerges from the restless play of quantum fields. Observations do not merely confirm or refute these ideas. They inspire new avenues of thought, new ways to frame the questions that have driven physicists for decades. In the quiet data of distant galaxies and the faint glow of ancient light, we find not just answers, but provocations, hints that there is more to reality than we have yet imagined. These clues, scattered like stardust across the sky, call us to look deeper, to listen more closely, to remain open to the possibility that the universe is stranger and more beautiful than our current theories can express. The search for quantum gravity's observational signatures is a testament to the patient, cumulative nature of science. It is a reminder that even the most abstract ideas must ultimately find their home in the world of experience. Each observation, no matter how faint, is a note in a cosmic symphony, a hint that the music of the universe is richer and more layered than we have yet begun to understand. As we stand at the threshold of this new frontier, we are guided by both humility and wonder. Humility, because the universe has always proven more subtle and more intricate than we expect. Wonder, because in every observation, no matter how distant or faint, we find the possibility of revelation. In the interplay of gravity and quantum fluctuations, in the ripples of space-time and the shimmer of ancient light, we see not just the universe as it is, but as it might yet become in the fullness of our understanding. The journey to uncover the observational clues of quantum gravity is far from complete. It is a path that winds through the quiet corridors of theory and across the expansive plains of the cosmos. It is a journey of questions as much as answers, a testament to the restless curiosity that drives us to explore, to imagine, and to seek out the hidden harmonies that underlie the dance of the stars. In this search, we find not just the promise of a deeper understanding of gravity, but a reflection of our own place in the grand story of the cosmos. We are creatures of stardust, born of the same quantum processes that shaped the first moments of the universe. As we listen for the faint echoes of quantum gravity, we are listening to the quiet song of our own origins. Echoes that remind us that we are woven into the fabric of the cosmos, participants in its endless unfolding. In that quiet listening, in that gentle seeking, we find not just knowledge, but a profound sense of belonging to the boundless mystery that is the universe itself. Thank you for joining this exploration of quantum gravity's hidden world. May the subtle echoes of gravitons and the quiet shimmer of quantum fluctuations remind you of the infinite wonder that surrounds us all. If you're still awake, feel free to continue this gentle journey by exploring our next video. Otherwise, let these calm thoughts carry you into a peaceful sleep, knowing that the mysteries of the universe are always waiting for you to return. Sleep well, and sweet dreams among the stars.